Thanks for being here.
Thank you for having me. This is awesome. Thanks, everybody, for joining me today. What's going on here? Very good. So based on the previous talk, I learned I should have created a talk about serverless blockchain AI. But unfortunately, I will only talk about AI today. And AI has been exciting. It's transformational. We're seeing a tremendous trend where AI is making a difference every day in our lives, where the most differentiating experiences that we engage with every day use artificial intelligence. And it's been exciting to be part of that trend. And as we see it today, what we're experiencing is a resurgence of AI. If you look at the several last decades, and I want to tell you that this plot I'm going to show you is to scale. The hotness of AI has only been going up. But we've gone through a low around the 90s and 80s. And there's been a tremendous change for that. And let's talk about how that came about. For the longest time, AI was about rule-based systems, where you took some input and you had a hard-coded set of, say, if statements, and you made some prediction. So for example, if you had a translation system that went from Portuguese to English, you might have an input like futebol, and you have an output like, and you know that's wrong. So you want systems that don't do that, that learn from data. So the big change in AI has been a shift from rule-based systems to machine-learned systems, where you take data and you learn a model that helps you make predictions about how the world works. And it's hard to pinpoint when that started, but I love this example from 1957 from Rosenblatt. This is called the Rosenblatt's perceptron. This box you see on the right is actually a camera. It has 20 by 20 pixels, so that's 0.4 kilopixels, almost the same as this phone I carry in my pocket. And he showed that camera pictures of triangles, circles, and squares we see on the top right of the picture. And he moved some potentiometers with motors in the back and learned to predict what was a triangle, a circle, or a square. It's amazing. Machine learning in action. Now, this shift from rule-based systems to systems like this to learn from data has been going on very actively over the last 20 years. And a good example of that change is what happened with board games. So about 20 years ago, IBM built this amazing system called Deep Blue that beat Kasparov in chess. It was a really incredible system. It was basically a rule-based system, represent the rules of the game, and used a tremendous amount of computation to explore all the possibilities and figure out what move to make, and did really well. But for a game like Go, where the set of possibilities was much larger, it was much more difficult to build a system based on search like this one, and took us about 20 years to come up with something that could build a world master, that could beat a world master. And that was what happened a couple of years ago with a system called AlphaGo. They used machine learning. It looked at the board configurations and learned from those to predict what was a good board configuration to move towards. So this is another example of the shift from rule-based systems to machine-learned systems, and that's what's been driving this shift and hotness of the AI. But the second piece I want to put in this plot, just to be clear, is that even though the buzzwordiness of AI has gone up and down over the years, I believe that the incredible value it provides to our users and to people around the world has only been going up. And it's been steadily and monotonically growing. It's really exciting to be part of that. And this shift over the last 10 years or so, this resurgence of AI has been driven by three things. First, availability of massive amounts of data, initially from the web and now through sensor data and much more. The availability of cloud, which is what we're going to talk about today, and large-scale computation. And as an academic, I must say, about 20 years of pent-up research that was totally ignored. So these driving forces have been changing what's happening in AI. And today, I will talk briefly about 4 trends I can see in AI systems that I believe will influence work like what you do in the cloud space. And I think about this as back to the future and rediscovering, just like we're rediscovering much of AI today. So briefly, The first one I think about is the shift to high-performance computing type workloads. In the 80s, we did a lot of high-performance computing type workloads, but more recently, there was a shift to massively parallel workloads, like what we see with Hadoop, Spark, and other systems. And what these workloads look like are things where you have a really, really massive data set, but you do very little computation per data element. Maybe you count the words in that data point. And this is amenable to massively scaled out systems with commodity hardware. And because you have a large number of machines, fault resiliency has been one of the big things you talk about a lot. However, the kinds of deep learning models you are building, like this one that we built for dealing with LiDAR data, are very complex and very computationally expensive. And they have to do a lot of thinking per data point. And so you're going to see, in addition to the workloads like the Spark ones, which are not going to go away, they're good to dealing with large logs of data and getting through the first phase, you're going to see other workloads where you only have huge data sets as opposed to massive data sets. And you have large computation per data point. And this leads to workloads that look a little bit more like high-performance computing that we had before, where you do a lot of computation in a node, where you have fewer jobs, and you need really, really beefy hardware like massive GPUs. And this is the kind of workloads that I use every day, and the ones that are making a difference for the applications that we're seeing, like speech recognition systems, image analysis, and so on. Now, in that context, we're seeing a second trend. In the 80s, we saw a lot of specialized, early 90s, a lot of specialized hardware. So every company will design their own chips, their own hardware to deal with compute. But as I mentioned with the kind of Hadoop Spark workloads, there was a move to commodity hardware. But because of this real large-scale computations we have to do in these kinds of deep learning models, we're seeing a lot more specialized hardware, be it fancy GPUs or new things like this is Google's TPU that can do training in the cloud in the large scale for the deep learning type workloads that we do. Or the chip that we deployed in the phone last year, the A11 Bionic chip, which includes a neural engine. So this is special silicon dedicated to machine learning models. And we're going to see more of that. We see, for example, Azure and Amazon using FPGAs in the cloud, exactly for the shift towards more specialized access to hardware. And in this context, we're faced with a new challenge. The challenge here is that we have even more hardware targets than we had before. And on top of it, there's a number of different machine learning libraries that people are using around the world, like TensorFlow, MXNet, PyTorch, CoreML, and others. And what you have to do is for every library, for every model that you create, you have to figure out how to target each one of these pieces of hardware. And this is a really hard and time-consuming engineering problem. To address this problem, I'd like to mention a piece of work from the University of Washington called TVM, which is done by an incredible number of talented students that's having massive adoption in industry, with contributions from folks like Amazon, Intel, Huawei, and other big companies. And this project allows you to easily connect machine learning libraries like TensorFlow, MXNet, PyTorch, with a wide range of hardware targets. It provides an abstraction, end-to-end abstraction, that includes how do you optimize the computation graph, how you express the tensor computations that are involved in this, and how do you schedule the optimizations on hardware. And this facilitates a lot of the underlying process of connecting libraries to hardware. So let me give you an example how this is made possible. So if you think about schedule optimization, we have to think about really low-level things like threads and loops and cache and tuning, all these billions of possible options which are typically done by hand. So every library like CUDA from NVIDIA tries to tune and optimize this by hand. And what TVM does is uses machine learning to automatically learn what is a good set of parameters that provides good performance in each one of these hardware targets. And it's pretty amazing what it can do. It's exciting that we have this academic project that's having massive adoption, but I want to remind you that it is an academic project. So let me show you what the setup looks like. This is what a lab looks like. And we're using a lab like this, we can do thousands and thousands of experiments on each one of these hardware targets and beat hand-tuned, state-of-the-art libraries that were created by these hardware systems. So for example, here what I'm showing is, in the x-axis, the number of trials, so the number of times we try out a different set of parameters on, in this case, an NVIDIA GPU. And I'm comparing the performance against cuDNN, which is NVIDIA's library for optimizing neural networks on GPUs. And we can see that initially our performance is not as good, but with a number of trials, we can beat the state-of-the-art hand-tuned cuDNN by about 20%. And in fact, we can do this across GPUs. We can do this with ARM CPUs, mobile GPUs from ARM and others, FPGAs, and more. And this is really exciting. And this is why this project has been getting a lot of traction and seen a lot of adoption. And I expect you'll be seeing more of it as more and more companies start to adopt TVM. So if you're excited about this, you can check it out at tvm.ai. So that's the second trend towards specialized hardware and being able to scale up deep learning to massive data sets. And a system like TVM can make that easy. The third trend I'd like to talk about is a focus on simplicity of adoption of machine learning systems. For a long time, we have used simple machine learning systems, but with deep learning, we try to provide more flexibility so you can solve more complex problems. And that has impacted adoption, because deep learning requires lots and lots of data, lots of domain expertise, complex training tools, and lots of GPUs. And that makes it really hard for anybody to adopt it. And of course, cloud services like we heard Azure, AWS, Google Cloud can make access to compute easier. And libraries like TensorFlow, MXNet, and PyTorch can make development and training tools easier, but you still need lots of data and lots of domain expertise, which makes it harder for developers in general to adopt machine learning systems. And this is something that's been hard to address, and something that I've been thinking about and that our company thought about before we joined Apple for many years. And here are two trends that I'm seeing in industry in general and how they will have impact in the space. The first one is about pre-trained models. So for tasks where data from the world can be used to train a machine learning model, we're seeing those as being commoditized and offered as services by folks like Microsoft, Amazon, and Google, as well as embedded into devices like the ones that Apple generates. So this is Apple's vision framework that's accessible to developers on every device. So for example, if you want to build an application that does optical character recognition, recognizes faces, or tracks a face's movement, we can do that out of the box without knowing any machine learning. And this has empowered developer creativity in an amazing way. But this is, of course, only possible for places that don't require your specific data for your specific problem. If you want to solve your specific problem with your specific data, you typically have to use existing machine learning tools that require a lot of expertise. You have to know what a deep neural network is, or sport vector machine, or one of these other systems. So something that we've brought together, which we call Turi Create, is a library for developers that, rather than focusing on models and buzzwords, it focuses on the tasks you want to solve, like image classification, or object detection, or recommender systems, or activity recognition. And uses something called transfer learning to be able to learn great models on small data sets. So let me show you what's possible. With just a few lines of code like this, you can load your data, train a model, and deploy it on, say, a phone in a very easy way. So a developer like here, Zach, friendly developer in our team, has no machine learning background, can build a dog detector with a few lines of code. And the key line here is this one where we say object detector.create. Now, Zach has other interests. So in addition to an object detector, he wants to recognize activity from sensor data. By just changing that line to object detector.create to activity classifier.create, he can create a 2018 version of the famous clapper, now using an iPhone. And detect that gesture and train it. And with changing another line of code from activity classifier to style transfer, we can create a new kind of computer vision system that takes an image like this one and a style, so other images like the ones in the bottom, and reinterprets the image using the style of the image in the bottom. So watch this video. So reinterpreting that image in a wide range of different styles, and you can train your own style. That's called neural style transfer. So there's a large number of tasks like this where you might want to train with your own style or your own gesture or your own type of image. We can do that with just a few lines of code. And by doing this, by making machine learning models commoditized and training commoditized, we can empower the creativity of developers that can solve problems that we did not expect before. And what I'm going to show you next is what a developer was able to do on their own and solve the problem that I've always had. So I couldn't solve a Sudoku puzzle to save my life. But thanks to Magic Sudoku, we can use ARKit to detect the Sudoku, optical character recognition to interpret the characters, and then solve the problem in one go. And as the camera moves, notice how it tracks and shows you the Sudoku solution on the table using ARKit. This is amazing. I will show it again. As I said, I've dreamt of this. And I'm a math guy. So we can empower creativity in amazing ways by bringing these tools to developers around the world. Now, a lot of these tools have been inaccessible to a lot of people. And one thing that I care about a lot is inclusivity. And inclusivity can mean many things, and there's a big trend around machine learning in the AI space to think about inclusivity in the world. And it can be making the tools accessible to more people, but it can also mean understanding how these black boxes really work. So sometimes they feel like this. The system might work, but you never know how it was even possible. And if you're a doctor trying to make a life or death decision, you want to understand why a prediction is being made and what impacts it has on that particular patient. So for example, if you have a system that says, this patient has cancer probability 0.9, the doctor is going to ignore that. But if you say, look at these related cases, look at these latest studies, look at these MRI results, and that's where we're making a prediction, then we can have much more confidence in what's going on. And in work from my student Marco Ribeiro from the University of Washington and former postdoc Samir Singh, who is now a professor at UC Irvine, they really looked at providing more interpretability to any machine learning model. And the picture is really simple. Let's say that I give you as an input a sentence that says, easily best sushi in Seattle. And I give it to a sentiment classifier that might decide whether it's a positive or negative sentence. In this case, it predicts as a positive sentence about a restaurant. What an explanation system might say is, this sentence was predicted positive because easily best is associated with positive sentences. And this lets us interpret why a prediction like what we're giving to a doctor is being made. So in a more fun example, take this image and give it to an image classifier and say, what do you predict for that? So a state-of-the-art classifier, just like you, might get confused. And what an explanation system tells us is, with probability 0.32, it predicts as an electric guitar. And at the bottom, you'll see the part of the image that was important for making that decision. That's the arm of the guitar. With probability 0.24, it predicts acoustic guitar. And you see it's more focused on the body of the guitar. And with probability 0.21, it predicts Labrador. And you see it looks at the face of the Labrador. And these are the parts of the image that support that decision. And so providing more transparent explainability can help us make better decisions from machine learning models, but it can also help us understand when machine learning models fail. And I'll show you a couple of really fun examples and important examples here. So state-of-the-art machine learning systems today can do amazing things, like take this image as input and ask the question, what type of road sign is shown? And it says, a stop sign. That's awesome. That's impressive. From image and a textual question, it answers the question stop sign. Or from this passage of text, you ask, how long is the Rhine River? And it says 1,230 kilometers. And you look at this and you say, wow, AI systems today, they're so smart and so impressive and so awesome. Yeah? But they tend to be brittle. So what Marco's work showed is that small perturbations to the system can really make them fail. So for example, in the top image, if I change what type of road sign is shown to which type of road sign is shown, we now get do not enter. Doesn't look so smart. In the bottom one, if you change how long is the Rhine River to question mark, to how long is the Rhine River, question mark, now it's more than 1,050,000. And so small changes in the input can really impact the predictions that are made by machine learning algorithms. And in fact, if we take these inputs and change what to which, it reduces accuracy by 4%. If you change question mark to question mark, it changes the accuracy by about 3%. And these are significant numbers. And what Marco's work is able to do is automatically discover these issues and improve the performance of the model. And at the core of these issues, the core challenge here is the data. The challenge here, there wasn't enough coverage in the data. There wasn't enough questions that started with which. There wasn't enough questions that ended with 2 question marks. And that led to challenges. And this is where I want to end with a thought and an example, where we have to remember that the data that you use is not this abstract thing. It's something that will define the user experience in a significant way. And let me tell you about an important example of how choosing the right data can make a tremendous difference. Between the 40s and the 90s, film companies, so the ones that made rolls of film, had to calibrate their labs from around the world as to how their images should be exposed and how the chemicals should be mixed to expose their images. And they created these cards, which they called the Shirley cards, based on the name of the first model. And later on, they're all called the Shirleys. You see a bit of sexism right there, to help calibrate these lab mixes from around the world. And all of these cards were typically light-skinned women, which meant that if you're a light-skinned person, the exposure for your images looked great. However, when you have photos of people with darker skin, you see overexposed pictures that did not look good. And this issue is clear when you have a picture that combines light-skinned people with darker-skinned people. And this issue is terrible, and it's disappointing. And it's really an impact of the data we use to train the system to help tune those chemicals. And it wasn't until the 90s when the dynamic range of the film increased, and they started having cards that included people with different skin tones, where we started to address this challenge. So the data that we choose impacts not just the quality of our system, but it also impacts how inclusive it is. And it's not just about having diversity and coverage in your data. There's been many studies that have shown that if you just train a machine learning system from data randomly sampled from the web, you end up with a system that is racist, misogynist, and sexist. And that's just a mirror to our society. So it's not enough for us to just think about the data that we choose, but we have to think about how that data reflects the culture and values that we aspire to. And with that, I think a trend that I am seeing and I'm hoping to see more of is to not just think about the business metrics when we're building these machine learning systems, but also think about the social impact and the human impact it'll have. in terms of fairness, in terms of transparency and being able to explain predictions, and of course, in terms of the respect that we have to each individual's privacy and their data. Thank you.
Thanks, Carlos.
Thank you very much.
Yeah, thank you, Carlos. That was great.